Okay, so hello everybody, my name is Richard. I'll welcome you to today's webinar about the preparation of geometry for simulation together with SimScale and with Ben from Custom Machines. I hope everyone can hear me. If you have any technical problems with the screen sharing or with the audio, you can at any point raise your hand or ask a question and we'll try to figure that out. If you cannot hear me, and then it's difficult, but you could also dial in via phone. I'll write that in the chat so that everyone can see that also. And then we'll start with the actual presentation in 2 minutes. Okay, so once again, hello everybody, and welcome to today's webinar together with SimScale and Custom Machines. Today we want to present you methods how you can efficiently and effectively prepare your geometries for simulation. We described this on a hands-on example that Ben Lewis from Custom Machines prepared, and he will also introduce you to all the concepts that he uses or used to clean up the geometry and generally uses to prepare geometry for the simulation. And yes, so my task is a little bit on the side. I will just introduce you to the general concept of SimScale and our new consulting partner program, and then I will pass on the word to Ben, and he will show you how you can prepare the geometry for simulation using SolidWorks. So I think we don't have any technical problems. Everybody can hear me. So let's start. Okay, so first of all, I want to introduce you to Ben Lewis, or better, let's introduce him by himself. Hello, Ben. Can you hear us?
Hello, Richard. Can you hear me?
Yeah. Okay. All fine. So then, Ben, please, could you introduce yourself? That would be awesome.
Yeah. So Richard, thank you for this opportunity to participate in this webinar. It's an honour and a privilege to be involved, and hopefully it's an opportunity to give back to the SimScale community. So my name's Ben. I'm the Managing Director of Custom Machines. At Custom Machines, I do industrial machine design, and so that means some CAD work, some simulation, automation, and also data acquisition, and that's primarily strain gauging and stress analysis work. I've been doing this for 15 years now, and I've been using SimScale for 2 years and SolidWorks for 8 years.
Okay.
Back to you, Richard.
Yeah, thanks, Ben. Thanks for having you on board here today. and for all the work that you've done to prepare this this webinar. Let's introduce myself. So my name is Richard. I graduated in mathematics and science and engineering here in Munich. I have my most expertise in the mathematical application in the application side on optimization methods or fluid structure interaction, and also a lot of experience in nonlinear analysis generally. Here at SimScale, I'm responsible for the solid mechanics side, senior engineer here, and yeah, my job is basically to try to make SimScale a product that has the best solid mechanics experience that you can get, and we'll hope to ship that all the time, and improving this with additional work that we do with webinars, and help you people to really succeed with SimScale and use this in a professional daily work environment. Okay, so I guess most of you already know SimScale and what's the idea behind that and how it works, but perhaps some people are new here, so I quickly introduce that also. So what SimScale is different from any other CAE tool is that we are completely browser-based. So you don't need any hardware or any software installation on your local PC or laptop to run really complex analysis. So you're completely free from any hardware costs that you would normally need to invest to get really large machines where you can run all those complex simulations. So it's very cost efficient. You do not have any large upfront costs if you want to start with simulation, and it's a very scalable approach. So you only pay for what you need. If you need more core hours, you can add additional core hour packages. For example, you can use larger machines as you need, or only smaller machines if you have only smaller simulations or smaller projects. So it's a very scalable approach. And also SimScale is the first place ever for simulation which brings together the tools on one side but also the people on the other side. So we are a place where the tools also meet the expertise and experience of people that use them to create an environment where people can really learn from each other and also pass their expertise to other people. You'll see that also in our pricing model. We have a freemium plan where you can really completely for free use the whole functionality of SimScale, do fluid mechanics, solid mechanics jobs, wherever you like. And you pay basically with your experience. So these projects that you do in the free plan are also free to use for other users. So you create public projects where other people can have a look at, learn how you set up your simulation, which methods did you use to solve a specific problem or a specific application, and this really is one of the big pros of SimScale, that we bring really the people together and also the expertise. But yet there might be situations where this is not enough, and here comes into play our consulting partner program. So on one side we have SimScale, and we have the users that want to use SimScale for their daily work and for their production work. And sometimes there might be situations where you just need more. So you need, for example, more expertise in a specific domain. You need people that really are experienced in a very specific application. Or sometimes you just need the job done today or very fast, which you cannot do on your own. And there we have people that could help you, and this was the start of the consulting partner program, that whenever you face problems like the ones mentioned, or you simply lack experience in SimScale and you want to get a jump start with the help of some people who are really experienced with SimScale already. And then you could consult our partners that they will help you to succeed in your simulation or in your analysis. You can go, for example, to the Consulting Partner Program page, where each partner has his own page. So let's have a look at the Custom Machines page here. So we see that you can get to know whatever the experience of our consulting partner is, what are the main strengths, and then you can directly fill out the contact form and get into contact with our partners. And yeah, so this is the main idea, that you really bring together also the expertise level really on a new level here. Yeah, so that's the whole idea, and therefore we also try to involve our consulting partners, that they are visible to the community, that they know whom to approach if they need consulting work. And part of this is today's webinar, where our first consulting partner, Custom Machines, by Ben Lewis, is presenting some of his knowledge or experience to our users, also that we can get a feeling for his expertise and what he knows best, and how with which problems we could approach him. Okay, so I think we can now switch to Ben. Starting from here, he will go on with the presentation. Whenever you have questions, you can ask them. If they can be answered right now, I'll ask them to Ben, and he'll try to answer them. If not, at the end we'll have a short Q&A session where we can answer all those unanswered questions. Okay, so Ben, I'll pass the presentation to you.
Okay, thank you, Richard. Okay, so today I'll be using SolidWorks to demonstrate some of the techniques I use to prepare my geometry for simulation. But for those users who don't use SolidWorks, much of the techniques that I'll be presenting are also applicable to other CAD tools as well. So it will still be of benefit even if you're not a SolidWorks user. There's still lots of useful tips I hope that you'll pick up. So today I'll be using this gantry crane as an example to demonstrate how to prepare this geometry for simulation. This is not my own geometry. This was taken from a GrabCAD user who has kindly made this available for the purposes of this demonstration. He created this geometry in AutoCAD, and then I've imported this into SolidWorks to do the work. So it doesn't need to be a native SolidWorks file. In fact, in most cases, that would be typical to get the file in a format that's just the plain and no history with it. So just some background on this structure. It's you can see the man standing at the bottom of this structure. To give you an idea of the scale of it, it's about 18 meters wide, about 9 meters tall, and 6 meters deep. So it's quite a substantial structure. It would carry a load of something in the order of about 80 tons, I would expect. And there's two features of this geometry that are distinctive or important from an analysis point of view. The first is that it's a double girder gantry, meaning that there's two of these girders going across which the the trolleys rest upon, and that means that the load is picked from between those two girders, and therefore there can't be any structural members, at least in the centre section, between the two girders, so it needs to be open in the centre. The other thing that is of interest with this structure is the way the ends are supported. So the ends are almost identical, except that the far end here has a diagonal brace, which makes this end rigid, whereas the close end here is pin jointed at the top. And the purpose of this is because this gantry crane runs on rails and the wheels are they have a flange on either side to locate them onto the rails. It means that the rails don't have to be precisely have a precise width, and so the width of the rails can vary without applying a large load to the structure. So this structure here is able to pivot to accommodate any change in width. So this is the original geometry that I started with, and this is the geometry I used for the simulation. And so what we're going to look at today is the process of getting from this to this. It started with over 2,500 individual bodies, and it has a number of potentially problematic geometry. So 200 short edges, 200 small faces, over 400 sliver faces, and a really large rebuild time. I've got a fairly substantial computer, and my computer struggles with this model because it's has quite a lot of detail. Whereas in the simplified version, there's only 60 bodies, there's no problematic geometry, and it has no features to rebuild, so it's quick to work with. The first sort of most obvious step here is that I've eliminated any geometry that I don't need, or any bodies that I don't need. So the trolleys on top don't really add anything to the don't really add any value to the simulation, because we know that the load from the trolley will be vertical because the load is applied through wheels. So we can simplify simply by just removing that geometry and replacing it with a load in the down direction. Likewise with the supports at the bottom, these wheel assemblies are connected through a pin. Because they're connected through a pin, we know that the reaction forces must also be vertical, so we can remove those to simplify the geometry. Also here there's an obvious symmetry down the length of this crane, and so I was able to take advantage of that and only really model half of this geometry. But it should be noted that it's not just the geometry that needs to be symmetric, also the loads need to be symmetric. So if I was going to use some, say, racking or twisting of the structure, then I would need to model the full structure. Of course, I would model just the half, and once I had defeatured half of it, then I would just apply a mirror operation to then create the full geometry. So the next step is to then go into the defeaturing process, and defeaturing is really just removing any geometry that is not structurally significant. So in this case here, we're looking at this joint down here where this column meets another member at the bottom, and that's a bolted joint. Here you can see there's the bolt holes, and there's two plates that are sandwiched together. In the defeatured version, there's no bolted connection, and there's just a single plate here. And this is not always a valid thing to do, but in this case, because it's just a direct axial load and the bolts aren't pulling apart, we can make this simplification, and we try to remove as many features as possible without changing the structural intent of the geometry. So all these changes take time to do, and so the question is, why go to this trouble of simplifying? And the answer really is that preparing this geometry is an investment in that you spend some time up front and then it pays off down the track. So when you look at the full sort of cycle of simulation, there's the geometry change or preparation, there's the meshing, setting up your simulation with contacts and materials, and so forth. Then there's the actual processing time, and then there's the post-processing time. And each of those stages are impacted by the original geometry. So the simpler and the cleaner that geometry can be, the quicker each of those stages will be. And what it allows you to do is when you have a simple, robust, fast geometry, you can iterate much quicker. And so what I mean by iteration is you can go through those steps many times and you can try different, whatever it is you're trying to solve, you can try different approaches, and each iteration of those is quick because you're working with efficient geometry. So that's why you would do this process. So I just want to start off with an overview of what I've done in this process. So I've broken up the defeaturing process into 7 stages, and they're not really 7 stages of geometry preparation. It's just 7 arbitrary points that I've chosen just so that I can put numbers against them at each stage, and then I can show how the model has progressed through the process. So for example, at the start I simply just imported the original geometry. I changed the origin to an origin that made sense for simulation, and I reoriented it so that it was facing in a direction that I was comfortable with, so facing up and to the front and so forth. The next stage was to delete unwanted bodies. Then I did some merging operations, combining bodies that were the same material and they were structurally combined. Then there was a few stages of defeaturing, and then adding some geometry to prepare it for simulation. And then finally I purged out all the features to keep it as simple as possible. So here we're looking at the first metric is solid bodies. So initially I started with over 2,500 solid bodies, and then by the end of stage 2, which is deleting unnecessary bodies, I was down under 1,000, and then by stage 3, which is after the merge operation, I was down to 17 bodies. The next metric over here is new features that I've added, and this is really a measure of how much work I've done at each stage. So initially there's not much work at all, and then in the final stages that's where the bulk of the work is done. And then over here we're looking at the rebuild time. So you can see to rebuild this model initially took over 300 seconds, and then once I got down under 1,000 bodies it comes down to less than a second. So it's really important to get the number of bodies down to a manageable level. And then at each stage as I've progressed, I have saved the file out as a Parasolid file and then re-imported it back in again to clean out my history tree, and that keeps my rebuild time low at each stage. Here's some more measures, and these are measures of potentially problematic geometry in the model, and the purpose of showing this is to show that things get worse before they get better, or typically that's a normal sort of part of the process. So here I've started with just over 200 short edges, and then after the merge operation I've introduced almost 600 short edges, which I've then had to go and remove. Small faces increased it after the merge, sliver faces increased, and so forth. So that's a normal part of this process. Merging creates problem geometry, and then we have to go and remove that. So when I'm preparing geometry for simulation, I don't work in assemblies, I work in multi-body parts. So I'll take an assembly, which is typically a manufacturing assembly, and then I will convert it to a multi-body part. I find it much more efficient, and there's just many more tools that I can use in multi-body parts. It just suits the process much better. And as I said, I regularly save out to a parasolid and import it again, because what I find is, particularly with geometry this large, is the history tree just gets unmanageable, and it can bog the system down. So I just keep it lean by purging it using export to parasolid. So before I jump into the full model, I'd like to start off with a trivial example, because I find that with trivial examples it's easier to get a concept across, and then I'll move to the real life example, because real life is not trivial and it's good to see both. So here we need to pretend that this is a manufacturing model, so it has it's an assembly, and it has two parts, and as would typically happen with a manufacturing model, there's a gap between the two parts, and so if I was to take this directly into a simulation, then I would need to define materials for both of those bodies, and I would need to define a contact between the two bodies. And for two parts that's okay, but for thousands of parts that becomes completely impractical. So what we need to do is merge as many of these bodies together where it makes sense to do so. So my first step would be to take this assembly and then save it out as a part file, and I'll call it assembly 1 as part. So now I have my two bodies, but it's a part file, and the two bodies are shown in the list of bodies here. And now what I can do, and what would be typical at this stage, is to extrude one of the bodies up to the other. And it's important to always be aware of this merge button over here. So if I tick the merge button, then I get one solid body now. So instead of two, I have one. Or I could untick the merge and I'll get three bodies, because the extrusion I've created is not joined to either of the original bodies. Or I could join it to one of the bodies. So I could say merge, and then I could select manually which one I wanted to merge to, and now I have two bodies, but they're separate here. In this case, we want all of the bodies merged together. So that's the general idea, except that the way it is in real life is that this wouldn't be neat and square like this. What I would have more typically is something that's on an angle, say, like this. And then if I do my extrude operation, or combine, then I'm left with this sliver face and this short edge in here, which is where the merge operation creates all these small problem faces. And so what I need to do is remove this face, because this face, when the mesher comes through, the meshing operation will put a disproportionately large number of nodes down this edge, and that increases the complexity of the mesh but adds no value to our results. And so in some cases it may not even mesh at all. If it's fine enough, it may even cause an error. So we want to get rid of as many of these problem areas as possible. So in this case here, I would take this face and this face and do a move operation from vertex to vertex. in the direction of this edge. So now when we look at this joint, there's still two faces because the angle still exists, and that might be important. But we've maintained all the important things. So we've maintained the thickness through here hasn't changed, the angle hasn't changed, but we've just removed the geometry that may be problematic. So that's the idea. So it's fairly straightforward on a model as simple as this to just visually inspect the model, identify the areas that are problematic and fix them. But in a model which is more complex, like this one, it becomes impractical to find all these problem geometry areas, and so we need a tool to do that. So this model here is not the original geometry, but it's not the finished geometry either. So if I go back to my presentation, it's at step 4 here, so it's about halfway along the process. It's after all the merge operations have been done, but it's before the bulk of the defeaturing has been done. Sorry, I'll just go back to SolidWorks here. Okay, so SolidWorks provides two tools that we can use for identifying problem geometry. One of them is the geometry analysis tool. It's part of the SolidWorks utilities add-in. So if you haven't used it before, it's you go to add-ins, SolidWorks utilities, and that should be turned on. Now that comes with SolidWorks Professional, so it doesn't come with SolidWorks Standard. If you're using SolidWorks Standard, there's another tool that you can use, and it is the check entity tool, which is this tool here, and I'll explain that one later. They're similar, just the geometry analysis has a few more features. So if we start with the geometry analysis tool, there's two areas that I use the most. So the first is the looking for insignificant geometry. So they are short edges, small faces, and sliver faces. So if we start with short edges, and I've chosen here the dimension of 4.9 millimeters because in this model there's a lot of thicknesses that are 5 millimeters, and I don't want to pick up all those plates that are 5 millimeters thick, so I've gone just under that, and anything under that could potentially be problematic. In practice, I would normally creep up on this number, so I would start with a small number and identify just the smallest geometry, and as I remove them, remove the problem geometry, I would increase that number until the geometry that it's identifying is geometry that I actually want to keep, and then I know that I've simplified the model as far as I can. It's taking a while to solve this. Wonder why that is. Normally it doesn't take this long, so we might have to do less of these. There we go. Okay, so it's identified 575 short edges, and if I zoom in, I'm not sure how slow your screens are updating, but you should see small little yellow dots, and each yellow dot, for example, this one here, each edge that is shorter than 4.9 millimeters is identified as being a short edge, and we can see that we would want to remove that short edge. If I expand this, I can see they're ordered from the smallest short edge to the largest short edge. So the smallest short edge is somewhere down here. So there's a really, really small short edge in here somewhere. And then our largest short edge is inside of this member in here. So I'm going to exit from that tool now, get rid of those two problem areas, and we'll come back. So this first short edge in here, if I click on this flange, we can see that in the combine operation, these three plates have merged with this end plate, but this bottom plate hasn't merged, and there's a slight gap between the two, which has created our short edge. And we can see on the other end, a similar problem has occurred where there's three plates that are all in plane, but this bottom plate here has been shifted slightly, and so it's created a short edge. So we can come down here, do a sketch, and extrude that sketch up to the end plate. And now we can see that that plate is merged properly, and we can do the same thing on this end here. This time I'll do a cut and extrude it, cut up to there. And now this is all one face. Similar situation over here. So if I look inside of this member, we can see the short edge that the edge check has picked up. This edge is 4.8 millimeters, so just under our 4.9 threshold. There's a few ways I could tackle this. The first way, most obvious way, would be just to simply delete the face and this one here, and then that will just merge the geometry in nicely like that. But this member has a lot of problem with geometry. It's got these short edges here, and these two faces are not level, and here as well. So there might be a better way. And if we look at this member down the other end of the structure and do a section through there, we can see that this geometry doesn't have any problems. So rather than fix the problem geometry, what I'll do in this case is simply move this one over to here. So if I select this body, I'll actually delete this one first. Delete body. And here I'll make a copy of this body, put it over here. and then I can position this more precisely by mating, I'll mate move this body and mate this face to this face. And if we can look, there is a slight problem, that is the pin is located in a different position, so we just need to extend this member out to the plane of symmetry here. So we can do that by selecting this face and then say move face up to surface. We'll pick our front plane and go OK. And so we've removed the problem geometry there. So if I run the geometry check, evaluate, or geometry analysis, and calculate again, so now we have less short edges, and now that our smallest short edge is on this member over here because we removed it from this one, and this has the same problem over here, and our largest short edge is now on a different member over here, and this one doesn't have any short edges on it at all. So that's short edges. Now we can look at small faces. I'll calculate that. So small faces, interestingly, are defined by a length dimension, not an area. So it's millimeters, not millimeters squared, and that's just how the algorithm works. You can look up exactly sort of how it works, but basically you just keep increasing the number until what it's identifying is actually a face that you want to keep. And in this case, about 16 millimeters was the right number. So again, it'll highlight any small faces, like in here, these two yellow areas are small faces we could get rid of. Up in here, there's a whole bunch of small faces. So again, it's ordered from smallest to largest. So our smallest small face is down in here. So, and I've already demonstrated that one, so I won't do that. And our largest small face is here. So I'll exit out of that tool, and to get rid of that, I would simply use the delete face tool, and it's gone. I won't run that again because it takes some time, or I won't run it on that small face one. The next one is sliver faces. Sliver faces are faces that are very long and slender, and it's important to get rid of sliver faces because they add a ton of nodes which are really of no value, or no structural value. Again, the 300 odd sliver faces it is found, it's highlighted in yellow, and if I zoom in, there's problems around these C channels here and here. If we look at our smallest sliver face. It's back down in here, and our largest sliver face is on this rail section here. So that would add a whole bunch of nodes in here which we don't really need. So if I exit out of that tool and again just delete this geometry which is not really important. I'm kind of deleting more than what the geometry tool, but I know that I don't need it. So so now I've got a much simplified representation of the I-beam, which is going to mesh much quicker and be much more efficient. So if I was to run that geometry analysis tool again, it would show that that is now no longer a problem. So that's insignificant geometry. We can also look at sharp edges, and there's or sharp angles. There's two types of sharp angles. One is knife edges and the other is knife vertices. So knife edges are acute angles that are formed by two faces, and knife vertices are acute angles that are formed by acute edges. And so we'll look firstly at knife edges. It's found 44 knife edges. Our smallest one is in here, and our largest one, which is our biggest angle, is over here internally in that frame. I'll look at this one, our smallest one. So I'll exit out of this tool. I want to show this one because it's a good example of a knife edge. So we can see here that this box section is formed by joining two C channels together, and at the point where they join, there is this knife edge created where the two surfaces are almost tangent to each other, and that could potentially be problematic for the mesher at worst, and at best it was just adding nodes that we just don't need. So I would also remove those. You can see that's a much cleaner representation of the original geometry. And the final one is knife vertices. (103) knife vertices. Smallest one's down in here, and the largest one is here. So you can see this edge and this edge have created a really fine point in here, which could be problematic. So again, I would just simply delete the face, and it just removes that problem. Okay, I had some other features. So there's let me just switch back to the presentation. So these are the tool. Almost all of the geometry preparation I do uses just these tools highlighted in red. I wanted to demonstrate some other techniques, but I can see the time's getting away, so I'm going to move on. But if I just describe in words rather than doing it, this frame here, oh, I've got the wrong frame. That's the final one. Yes. So in the original geometry, this frame was placed, or this bracing was placed not symmetrically onto the frame. So you can see here it's overhanging here, and there's a big gap over here. And so the technique I would use to fix that up is I would slice through here and here to separate these from the main body. I would then shift it across and merge it back in again. And that's a fairly straightforward operation, but I don't have time to do it right now. So, but if anybody's interested, I could explain that later. All right, so I need to move on. So once the geometry preparation is done, then obviously upload it to SimScale and do the meshing. So I've used the first order mesh set to coarse and on an 8-core machine, and after running that, it turns out to be about 1.4 million nodes and about 4.5 million 3D elements, and you can sort of, from these pictures, you can get an idea of it's quite a nice mesh. The simulation itself is fairly straightforward, except for just I've added these elastic elements at each side of the joint, and the purpose of that is to provide stability for the model. So if you think of, so this blue member down here, this blue member is connected to a fixed constraint, and so it's stable, but then the pin that sits inside of that blue member and this column here, they're not constrained apart from the physical contact between the pin and the column itself, and so you could visualize that as maybe rattling or the pin moving sideways, and so all that movement makes for an unstable solution. So in order to stabilize the joint, what I did was I added these geometric elements to each end of the pin. So this joint here is a section through the pin, and we're looking at this joint here. So if I section through that joint, it looks like this, and those red discs at each side of each end of the pin are there to connect all 3 elements in that joint together. So we have an outer clevis, we have an inner clevis and a pin, and they're not physically connected to each other, and so in order to stabilize that, what I've done is added this element here, and then with 3 bonding operations. So the first one is the green one. I've bonded the donut area to the outer clevis, and here I've bonded the inner part of the donut to the pin, and here I've bonded the back of the stabilizing element to the inner clevis, and that holds all 3 elements together so that they can't move any significant distance. But what I've done is I've defined the stiffness of this material to be comparatively very weak compared to the structure, so it has a stiffness equivalent to rubber. And what that means is it can't really carry any load, so it doesn't change the stress results, but what it does is stabilize the joint. So apart from that, most of the simulation setup is fairly straightforward, and it's a public project, so in your own time you can have a look at that, and if you have any questions, feel free to ask me on the forum, and I'm more than happy to talk about that. And this picture down here shows the deformed state of that joint. So you can see that the center of the rubber element here has moved with the pin, the outer face has moved with the outer clevis, and the inner face has moved with the inner clevis. So just quickly, here's the results of the simulation. This is a deflection plot, so this plot shows pretty clearly that the pin joints here are working really well. So the grey is the original geometry, and then the coloured version is the deformed or the simulated geometry, and you can see that this joint here is working correctly, and then over here this triangle section is rigid. We can see the stress profile. Interestingly, in the original geometry, these diagonal members are hollow, whereas this half of the structure has solid members, and so you can see clearly that the hollow members are significantly more stressed than the solid members. I'm not sure if that was intentional, but that's how the geometry was, so that's how I analysed it. You can see the pin joint, the detail of the pin joint here. So we have a high compressive stress coming through on the inner clevis at the top, and then a compressive stress on the outer clevis at the bottom, and because they're offset, that creates bending in this pin, so we get a tension at the bottom and a compression at the top. And also we can see the compression and tension through these diagonal members here. And that concludes my presentation. If there's any questions, I'm happy to answer those.
Okay, thanks Ben. First of all, awesome presentation. I really learned a lot how to efficiently prepare geometries for simulation, and I think also all of our attendees really know that from day-to-day work that you in almost any kind of industrial application, any relevant geometry, you really have to first prepare the geometry, especially if you have a highly nonlinear analysis. You really try to reduce the amount of features that geometry has to relevant amount that's not too high and to lead to an unreasonable amount of simulation time. So yeah, thanks again for this awesome presentation. I'll get the presentation back to me. And if there are questions, then we could answer them now. Otherwise, I'll encourage all attendees to have a look on our homepage, check out our partner pages for the Consulting Partner Program. If you want to get in touch with our consulting partners, you can just fill out the form on the homepage or write a message to support@simscale.com, and we'll happy to make the contact. With regards to the model, I guess the best place would be to ask questions in the forum. If it's specifically about the model setup, the simulation setup, something like this. Yeah, I guess we guys are around there, happy to answer the questions. Yeah. I think that's it. Someone's asking if you have a convergence study done of the mesh. I guess it was not in the scope of this visualization presentation of it, or not?
Yeah, no, I haven't done that, Richard.
I guess, yeah. I think that could be done, but I think it would be too much for just a presentation to show on an example how to defeature the geometry to make a complete study out of it. But yeah, that could definitely be done, and normally that's a good practice to at least compare different meshes and to see if the results do not depend on the mesh itself.
And it's a public project, so anyone's welcome to take it and refine the mesh, and I'd be interested to see the results.
Yeah. Yeah. Okay, good. Someone's asking if you consider a circular member chassis in SolidWorks and perform simulation we get results by importing the same geometry in some CAE software requires contacts. How to do that? Did you understand the question?
No, the box is really small. I'm trying to open it so I can see the question, but I can't.
Okay.
Sorry, how do I make that bigger?
So yeah, so if the question itself is if you export the geometry and import it then to a CAE software, if you have to manually define the contacts there, probably this is the question.
If we consider a circular member chassis in SolidWorks and perform simulation, we get results, but importing the same geometry in some CAE software requires contacts. How to do that? I've got to say I don't understand the question, but happy to, I'm happy to answer that question if there's more detail provided.
Yeah. So normally if you do, I mean, a lot of CAD tools have their integrated solvers that perform like simple simulations, and normally they already can take into account the mating conditions, for example, that you defined in the geometry and use them to predefine contacts. So this could be the case why, for example, in SolidWorks you do not have to define contacts, but in some other tools, after you exported the geometry, especially to some neutral format like STEP, and there is no information left for on the context itself or the context definition, so you have to redefine them. So that depends on the tool if it's done automatically or you have to manually define that. I think that was the question.
Yeah, okay.
Okay, good. Okay, then there's a new question.
Yeah.
Did you see them?
Yeah, I see that question. I have a question, please. How do you set SolidWorks in a way that you can delete a face in a solid and it doesn't change it into a surface? Oh, yes, I understand this question. Yeah. And complete the solid.
Should I give the presentation to you again? So you want to show?
Yeah, sure. Yep.
Okay.
So the question is, so let me just put a feature in here. So if I do, for example, maybe a chamfer here. So what I was showing in the demonstration was deleting this. So this is maybe an unwanted feature, and I was demonstrating that you can delete that feature like that. Now, if I had selected just delete and not delete and patch, then what it leaves you with is a shell, because it hasn't patched it back up again and then formed a solid. So it's important when using the delete face command, you don't just delete the face, you have to delete and patch the face so that it forms it back into a solid again. I think that hopefully that's answered the question. Also, you can't just, how do I say, if I was to delete this face, for example, and try to patch it, it's not really going to work because it needs edges everywhere around the face that you're trying to. So if I just delete this face, it can't really patch it in any other way other than just putting it back to what it was in the first place. So you can't just use it anywhere. You have to. So in this example, where there's this chamfer, if I delete this face, all the faces around it can extend back to form a solid again. So that's important when you're using that feature. But I use this feature all the time. It's just so quick in defeaturing the geometry. So it's really it's an important tool to use.
Okay, thanks. I think that exactly answered the question. Okay, if there are no more questions, I think we can conclude the presentation here. So as anytime, if you have any questions, you can ask in the forum or write us an email. Comment on the public project of Ben, or in the forum or in the projects pages. And yeah, thanks once again, Ben, for this great presentation, and that you shared your knowledge with us. It was really helpful to get an insight how we can efficiently work our way through preparation of the geometry for simulation. And
you're most
yeah,
welcome.
Thank you very much.
Thank you.
Okay, so thanks guys. If you need any more information, just drop us a line. Thanks and bye until the next webinar.